Hello everyone. In today's class, we will discuss the correctness of CTL model checking algorithm. If you recollect, in the last two classes, we discussed the way I do this model checking of CTL properties, right? So, what we have seen, just to recap, we will take the adequate set. So, we have effectively taken AF, then we have taken EU and EX, right? So, we have taken these three. This is my adequate set, and then we develop algorithm for that. Let us see how we have done this algorithm, right? Or it is basically based on leveling the nodes, right? So, how do we have done this for AF? So, we will basically find out the node where phi holds, right? We have to do AF phi, right? The nodes where phi holds, and I will mark that nodes with AF phi, right? Why? Because future includes the present state. So, phi holds means in that state AF phi also hold, right? Because any path starting from that in the first state itself AF phi holds. So, I can say that AF phi holds in that state, right? And then iteratively what I do is we identify another state whose all successor has AF phi. Then I will also mark this state also AF phi, right? So, now see here we are talking about the correctness context. So, we already know that any node where I am marking the state with AF phi, the AF phi indeed holds there. So, there is no confusion about that, because we are starting from the baseline where phi holds implies AF phi holds. So, that node definitely AF phi holds, and then I am identifying another node where all successor has AF phi. So, that means if from this node any path going through this, it will go through like this, right? Now, I am saying that if for this state in all path here AF phi holds with means there will be some path from here where phi holds, right? So, effectively for that will be true here also, right? And it is for all path. So, effectively whenever marking a node with AF phi, this is indeed AF phi holds there. So, there is no confusion about that. So, that correctness is by construction or by the method itself, right? Then what is the correctness we are going to check here is basically you are actually started leveling, right? In what I am doing, we are starting from the nodes where only phi holds. So, I will get those sets. Then I am trying to identify the nodes from where all transitions coming to this set, I will add them, right? And then I will try to see the nodes from where all transitions are coming to these sets, and this is how I am growing the sets, right? The set is growing from the nodes where phi holds to bigger nodes, and this way I am going to level the nodes, right? And eventually I will reach a fixed point. That is very important. So, what we are basically saying that when I reach that, I am not able to include any node further, right? So, this is, let us say, my fixed point. I am not able to include any further node here. What does it mean? All the nodes where AF phi should hold is already leveled, right? I am not missing anybody, right? So, what I have to prove that if I just keep doing this, at some point of time when I reach this fixed point that I am not able to include any more node into this list, that means I am completed with leveling all the nodes with AF phi, right? So, that particular thing has to be proved. The leveling part is correct by construction, right? So, we will take the proof at the end, but I just give you the intuition of the correct, what do you mean by the correctness of this algorithm, right? So, similarly for EU, what we have done, we basically start with the node where phi 2 holds. So, I will basically identify the nodes where phi 2 holds, then maybe some 3-4 nodes, let us say, and then I will identify the nodes where phi 1 holds, right? Phi 1 holds, and there is at least one edge to some node in this set, right? Then I will also say here E phi 1 until phi 2 holds, right? So, this we have already discussed. So, this way I will include this node into this set and so on, and this way again I will continue, and I will continue until a state where I am not able to include any further nodes, and that is my least fixed point. And again I have to prove that this contain all the states where E phi 1 until phi 2 holds, and there is no further states available where this can hold, right? So, that is the correctness proof we have to show, okay. So, this E phi 1 phi 2 I have already talked about, that any states are phi 2 holds, there E phi 1 phi 2 holds, and then you find a states are phi 1 holds, and there is an edge to this state where E phi 1 phi 2 already holds, you mark that state also with E 1 phi 1 phi 2, right. So, this we have already discussed. Similarly, Ex phi is very simple. So, you have to find out the states are phi holes, and then you have to find out the states from where there is at least one transition to this. In this state, I will mark Ex phi, right, not in this state, because Ex is in the, there exists one next state where phi holds. So, for this node there exists one next state where phi holds, hence in this state Ex phi holds. Okay. So, this leveling algorithm we have already discussed. To explain this leveling algorithm on a practical example, I will take this mutual exclusion problem, which is very well known, where say there are two processes, they try to use the same resource, right. So, they want to execute their critical section, so they can only, one of them can be only executed at the same time, because they are using the same resource, right. So, in this case we try to model that problem first, and then I will see how do the leveling algorithm will work for certain correctness property of this mutual exclusion problem, right. So, the problem is that determine which process. So, basically there is a shared resource, only one process can access that shared resource at a time, and when they are accessing that shared resource, we will say they are in critical section, right, and determine which process is allowed to in critical section, that is the problem. Every process can be in 3 state non-critical section. So, they are doing something else, which is let us say n trying to access the shared resource T, and it is in critical section C, right. So, the current for every process, the process will be like it is in n, then it will try to access the shared resource, then it will be in critical section, then it will come back to n T, right. So, this may be for process 1, similarly sequence will be there for process 2 and so on, right. Now, let us try to model it for 2 such processes, right. So, you have 2 processes P1 and P2. So, this N, T and C I talked about here, N, T and C, they will become now N1, T1 and C1 for process 1, and N2, T2 and C2 for process 2, right. So, you have basically 2 processes and these 6 variables are there, and then what are the possible state can happen, this is what the possible states. So, at the start they both are in non-critical section N1 and N2, right, and then it might happen that T1 is process 1 is trying to access the critical section. So, it can move to T1 N2, that means process 1 is trying to access the critical section and process 2 still in non-critical section, right, it is in non-critical section, and then it might happen that this process 1 get the access of the shared resource. So, it is in critical section, right, or it may happen that at this process N2 also started, process 2 also started to access this critical section. So, we can either move to T1, T2, both are trying to access the critical section, or still process 2 in non-critical section and T1 get the access C1, right. After this, in this state, it may happen that it complete the critical section operation and it move back to this state. So, C1 become N1, or at this state also process 2 can ask for critical section. So, it may reach to this section C1, T2. Similarly, in T1, T2 either it T1 get access, then it will move to C1, T2, or process 2 get the access. So, then it will move to T1, C2. It means process T1 is trying and process 2 get the critical section, right. So, similarly at the start it go to N1, T2, from there N1, C2 and so on. So, this is how I am basically constructed the possible state transitions, right. So, this is the kind of modeling of the mutual exclusion problem, right. So, this is the Kripke structure or transition system for me, right. Now, and let us say here I will just give you a simple example. Let us say I want to check E T1 until C1. Let us say I try to model level this, right. So, how the process will go? So, everywhere wherever C1 is true, I will say E T1 C2 is true, right. So, let me clean this diagram. So, so here you have C1, you have C1. So, here I will write E T1 until C1, right. So, because here C1 true, so I can write this. Similarly, here also I can write E T1 until C1. So, in this case this is true, right. There is no other state where C1 true. So, only this state I level at the start with this, because if you see here that E labeling algorithm for E until is that any, so if you are trying to do it for phi 2, so any state where phi 2 holds, I will do phi E phi 1 until phi 2, right. So I model this, and then what is the rule? I have to identify the states where T1 holds. I have 3 such states. This one is one state, this is another states, and this is another state where T1 holds, and the rule is that there exists one next state where E T1 until C1 holds, right. So then, and this is the case here. So this state also I can label E T1 until C1, right. For this case also I can label same way, because there is T1 holds here and there is a next state where C1 holds, it's E T1 until T2 holds. So this state also I can encode as E T1 until C1. Now take this state, the next state is this, right, and here already E T1 until C1 it holds. So this state also I can now encode as T1 until C1. And now there is no other state where T1 holds. So these are the 5 states where this particular property holds, right. This is the labeling algorithm for E T1 until C1, right. And if you say the start state is this, and since this start state does not belong to this my label, then I will say this model does not satisfy, let us say this is my S0, S0 does not satisfy E T1 until C1, right, because I start labeling the nodes and I identify the 5 nodes, right. So these are the 5 nodes, this nodes, this node, this node, this node and this node, these 5 nodes are labeled with E T1 until C1. So I will do this, and then I found that this the node starting node is not labeled with this. So I will say this model does not satisfy this property T1 until C1, right. So this is how this labeling algorithm works, okay. So I will take these safety properties. So this mutual exclusion of these properties, like both process cannot be in the same critical section simultaneously, right. So which is basically A, G, not C1 until C2. Similarly, liveness property is that whenever process 1 requests entry to its critical section, it eventually enters, right. So that means all globally, if T1 happen, in all future C1 should happen, right. So this is the liveness property, and also it has non-blocking property and no strict sequencing property. So we will not taking them here for discussion. Now let us see, I want to label the node for this property, and we will check whether this property is satisfied by this model or not, right. So so the property that I am going to label is this, but since I am only taking the adequate set AF, EX and EU, I have to rewrite this in terms of this, right, and this is what I have done here. So this AG can be written as not of EF and not EG, right. So it is basically AG phi equivalent to not of EF not phi, right. So this is what the property. So this is what I have done, and then I do the Boolean manipulation, and then I finally get this E not E true until C1 and C2. Okay, so this is I can encode this because this has E until, right, which is part of this. Okay. So now I will show you how this labeling will happen here. So what I have told you in the classes, when you have bigger formula, you have to take the sub formula first, right. So what I am going to do, I am going to take this sub formula first and try to identify state where C1 and C2 both holds. But if you see here, there is no state C1, C2 together, right, because both cannot be in critical section. So that state does not exist. So none of the state will be labeled with C1, C2, C1 and C2, right. Now because now I am going to check this E true until this. So this start with that the states where C1 and C2 holds, but I do not have any state where it is holding. So I can say that E true until this. So E true until C1 and C2, this does not hold in any of these states, right. Then but so this does not hold, it means the negation of this holds in all state, right. So that means if this property is say phi, I will say phi holds here, phi holds here, phi holds here, phi holes here, phi holes here, phi holes here, all states, because E true until C1 C2 does not hold in any state, that means negation holds in every state. So I will say that this mutual exclusion, that only one both process cannot be simultaneously in the critical section, it holds in this state, because it even the start state is level with the phi. Okay. So this is how the leveling algorithm will work for the mutual the first property, the safety property. Now let us take the liveness property, which we have already encoded like this. Again the problem is that it is a AG, so I have to take the negation of AG, which is basically not of EF of not this, right. So I just take not EF and not of this, and then I take this implication can be represented not, say A implies B is basically not A or B, right. So with this property I will get this, and then I this EF I can represent is true until false. So effectively I got this formula, which is in terms of AF and E until, right. So both are here. So this can be checked with the logic that we have developed so far, right. Now let us see how we can encode this. I can label this graph for this particular example. Again what I have told you, that we already know had C1, T1 and N1 holds, right, that already given. So what I have to do, I have to first take AFC1, right. So this is the sub formula AFC1. So now how I will say the states where C1 holds, AFC1 holds, right. So C1 holds here, C1 holds here. So I will write AFC1 holds here, AFC1 holds here. And now the rule was that if I identify some state whose all next state is state where AFC1 holds, I can mark that. Now I have to just check the successor node of this. For this node there are two next state. Here it holds, here it does not hold. So for this state it will not hold. For this node also there is two successor node. Here this it holds, but here it does not hold. So here also I will not hold. So effectively only these two states where AFC1 holds, right. Clear? Okay. So now what I will do is but here I have take the next part of the formula, which is negation of this, right. So I have just taken AF phi. So the states where AFC1 does not hold, those states negation of AFC1 holds, right. So basically here AFC1 negation of AFC1, negation of AFC1, negation of AFC1, negation of AFC1, negation of AFC1 holds in these 6 states, right. Now I have to check the formula, which is T1 and negation of C1. So all the states where negation of AFC1 holds and T1 holds. So there are 3 such states, right. So here T1, T1 and T1, but these 3 states where no T1 is there, right. So basically in these 3 states I will write that T1 and this hold, T1 and this hold, T1 and this hold. So this sub formula is already checked, right. So I have identified 3 such states where this holds, right. Now I have to check this E until true until this. So effectively I am checking if I am assuming this T1 and not of AFC1 is basically say phi 1, right. So effectively I am now checking E true until phi 1, right. This is the property I am going to check, right. So I know the phi 1 holds here, phi 1 holds here and phi 1 holds here. So other mark things I will just remove now for cleanness, right. So these are the states where this holds. Now what I have to, true is hold every state, right, true holds everywhere. So I have to check, how do we check this? I will check this by, I have to identify the states where phi 1 holds, right. So in these states I will say this also holds. So this let us say phi 2. So the states where phi 1 holds, I will say this E true until phi 1 also holds in those states, right. So, I basically here also phi 2 holds, phi 2 holds here, phi 2 holds here, right. You understood this, right. Now, what I have to do? I have to identify the states where true holds, which is every state, and then I have to identify the states where there exists a transition from those states to states where phi 2 holds, right. So, here phi 2 holds, this is the states where true holds, and there is a transition to this. So, I will say phi 2 holds here also, right. Phi 2 is this. Similarly, for this state there is a transition where phi 2 holds. So, I will say phi 2 holds here as well. Now, for this state there is a transition to state where phi 2 holds, I will say phi 2 holds here. Now, for this state there is a transition where phi 2 holds, I will say phi 2 holds here. Now, for this state there is a transition to states where phi 2 holds, I will say phi 2 holds here, right. So, effectively I identify all states where phi 2 holds. Okay. What is your actual formula phi, which is negation of, your actual formula is phi, which is negation of phi 2. What does it mean? That means there is no state where this phi holds, because in all state phi 2 holds, right. So, phi does not hold in any state. So, does it mean that this particular modeling has some problem? You see that. What does it mean? What is this property? The property is that if process 1 requests to enter the critical section, it will eventually enter. So, that means in all path, in all globally, in all path globally, that means in any state wherever T1 holds, from there all future path, in all path in future C1 holds. So, if I found some state, I mean some combination where you request for T1 but never get C1, that is the counter example, right. And if you come back to this example, let me try to take a different color now. You see this path, you have T1 here, and now you see this path, right. Let us say this is the path. So, this is say S1, say this is S2, this is S3. So, I have a state, right. So, let us say this is S0. So, I have a transition S0, S1 to S2 to S3, then again S1, S2, then S3. So, in this transition you see T1, T1, T1. So, you will never get C1, and this is infinite loop, right. So, I basically got a path in which even if you request T1, you are not getting the critical section C1. So, effectively this particular model does not satisfy this property, right, and this is the leveling algorithm also identify this, because none of the states where this phi holds, right. So, this is the kind of explanation we have. I hope you have now the very clear understanding of the how the leveling algorithm works, right. Similarly, I will give you this as a homework where you try to do this encoding. Again here you have AG, so you have to convert this into EF. Again from EF you have to convert them into EU, right. So, and then you try to do the leveling. I will strongly encourage you to try that at home. Okay. Now, let us come to the correctness. I will not give a very detailed correctness proof, I will only give you the intuition, right. So, what we have told earlier that this whatever the states where I am marking with some property, that is indeed correct there. So, there is no problem. The correctness we have to show that whenever I do this I get a fixed point, right, either it is a least fixed point or greatest fixed point, we have to make sure that I have covered all the states. There is no further state available which can also be marked with the same property, right. So, this is the only thing you have to do. So, the leveling algorithm so far we have seen is the kind of least fixed point. We start from the start thing, then you grow, and then you get a final node, right. This is called least fixed point. And for EG, we have discussed in the previous class that it is greatest fixed point. So, we start with the all state, and then I will try to remove some of the states. So, from this I will go to this set and so on, and finally I get this, and this is my greatest fixed point, right. This is the nodes where EG phi holds. Okay. So, now I will show that this is effectively correct, my construction. So, I will give you the only intuition. So, to do this I will introduce the function called monotone function. So, let us decide what is monotone function. So, it says that the function f is monotone function. It is defined over power set of a set. Okay. So, PS is a power set and PS is also power set. So, it is basically from one power set to another power set. I will talk about that, right. I will say this function is monotone function if I take two subset x and y, right. So, these are two subset of S such that x is subset of y. That means x has less number of element, right? Y is bigger set. Then fx is also subset of f of y. Did you get the point? So what I am saying, I have taken a small set. So this is x, which is mapped to some y, right? So it is basically fx, right? And it will map to some fx because this is the function, and let us say this is the fx. Okay. Now you have taken another set which is y, which is y where x is subset. So it is showing if it is the case that when it map to the sets, and this is fy, right, and where fx is also subset of fy, right. So if you map x to fx and y to fy such that fx is also subset of fy, then I will say this is a monotone function, and this holds for any subset x and y. Okay. So then I will say this is a monotone function. Now let us tell what is power set. Power set is basically if you give a set, let us say my set is have two elements S0 and S1. All possible subset of this is power set, right. So now for this, what will be the power sets? So PS of S is basically, P of S is basically there is no element which is null set. Then you can take only S0, you can take S1, or you can take both, right, S0 and S1. So effectively you have 4 possible elements in the power set, and it is basically 2 to the power n, right, whatever the number of elements in the set. So this is what is basically called monotone function. So effectively it is kind of keeping the incremental nature for the mapping part also, right. So now give an example of a monotone function. Let us take, I have taken the set S equal to S0 and S1, and I define the function fx, which is basically taking whatever x and it take union to S0, right. If it is happening this, so now I am taking two subset x and y, right, from this S, right. So x and y, which is subset of S. So where x is subset of y, let us say x is basically S0, right, S0, and y is basically S0 and S1, right. So this is subset of this. Now what I am saying, I am defining the function as fx equal to x union S0. I am just adding S0 to it. Now if we map this, what will be fx? Fx will be, what will be fx? S0 only, because S0 union S0, and here also I am adding S0 to it. So the f of y will be S0 and S1, right. So then still this fx is subset of fy, right, because it has S0 and it has S0 and S1 both. So I will say this function is a monotone function, okay, and this is not for only one subset, it should be true for every subset, okay. So what is our objective, why I am taking this monotone function? So our objective is to show that this EG, AF and EU, they are also kind of mapping, right, you are basically finding sets, subsets, right. So this functions are basically growing, right, it basically growing, it is starting from some small state and then I am growing, right. So again this fx will be subset of fy, right. So this concept should hold here. So that is what the objective, okay. So there is one more important point of a monotone function, that I will say some subset x of S is a fixed point if fx equal to x. So if I take fx x and I will map them using the function, I will get the same set. So then I will say this is a fixed point of the function, okay. So if you see what I am trying to say here, that I just told you what is the correctness objective. Our objective is to show that I eventually reach a fixed point, that I am not able to add any more thing, and that fixed point is basically the final set, right. I am not able to add any more item into this, right. So what I have to effectively show, the function corresponding to this EG, AF and U, they are monotone function and they have a fixed point, right. So if I show that, that means I reach a state from where I cannot add any further state. So that is the simple objective I have, okay. So this Cantor-Tarski theorem is on monotone function. It says that if you have a finite set of sets which has n plus element, n plus 1 elements, right, and the function is the monotone function. So that means it holds that property of x subset of y implies fx is subset of fy. is a monotone function, and then if I keep applying this function, so f n plus 1 means I am applying this function n plus 1 time, starting from this null set, I will reach a fixed point, right. You see, I start with null, right, then I will get f of null. There will be, since and then if I apply f of null, I will get another set, right. So, this is how I am going to grow, and then I will apply n plus 1, and this is a least fixed point, and if I start from the entire set, I will get to the greatest fixed point, and this proof is very simple, right. I will tell you. So, let us say I start from this null and I apply, I get f of phi, f of null set, and then I will apply f of, then f of f and so on, right. But now, because it is a monotone function, this psi, this null set should be subset of this, that means there will be at least one more element here than null, then f of phi should be subset of f of phi, again because this is a monotone function, right. So, this way if you keep doing it, for f to the power I will get some, I will basically get one more element from the previous element, right. Now, let us assume that I do not reach a fixed point, f k is not the fixed point. So, I try to prove by contradiction. So, if I say that f of k is not a fixed point, then what will happen? This is not possible, I will show that, because f of 1 have at least one element, because null set has no element, then f of 2 has at least two elements, then f of n plus 2 has at least n plus 2 elements, but your set has n plus 1 elements, because you are growing that set every time, you are basically growing by at least one number, and your total number is n plus 1, you start with null. So, after n plus 2 at least some element will be the previous element, right, which is already covered, right. So, that means I have reached a fixed point, I will not able to add any more elements to this, right. So, this is the kind of proof that monotone function will always reach a fixed point. So, this is I am starting from null. Now, if you think about that, I am starting from S, and I am basically applying such a way that it is in reverse direction. So, then I will get some subset S1, then S2 and so on, then I will get a fixed point, right. So, then if I keep applying this every time, if I remove at least one element, if I apply n plus 2 element, then I will at least, so I will get to null, I cannot have minus 1 elements, right. So, essentially that will be my fixed point, right. So, that is the idea. Now, quickly show that this, let us say I just take one of this SAT EG. If you remember how do you do the SAT EG, I start with the all states, right, and then I will identify the states where only phi holds, right, and then I will identify the states where phi holds, and there are at least one next state where EG phi holds, right. Then I will keep only that. So, basically I am syncing that thing, right. So, basically I start with this and I will try to sync that set. So, the corresponding function is basically is f x equal to the initial set phi intersection pre there exist x, right. That is what this whatever I talked about here. So, I have to first show that this is a monotone function, and then because monotone function has a fixed point, greatest fixed point or least fixed point, so this particular things will hold, right. So, what I will do, let us say I have taken two subset. So, what I have to show basically, if I take two subset x and y from this set where x is subset of y, I have to just also show that f x is subset of f of y. So, this I have to just show for this function, right, which is very simple to do. So, if I assume that there is some S1 which is belong to x, right, and there is some transition S0 to S1. Since S1 is belongs to x, implies S1 is also belongs to y, because x is subset of y, that is my assumption, right. So, so that means this is true. Now, if I do this pre there exist of x, right, what does it pre there exist? Is basically the set of all states, right, which at least one transition is going to set x, right. This is x, and pre is those sets for which say at least one transition is going to this, right. So, now I can easily tell that this pre there exists of x should be subset of pre there exists of y, because this y is bigger set of this, right, this is y, because whatever sets going to x, this will also part of this pre there exists of y, right, because this is already inside x, right. So, it may be this, right. So, this is pre there exist of y, and this is basically pre there exist of x. So, I can say that this pre there exist of x is subset of pre there exist of y, which is very obvious, right. Now, what I am doing here, I am basically the function I have taken is phi intersection of this. So, now if I take, so this is subset of this and this is same, right. I am doing an intersection of this, right. So, then what will happen, this is my f x. So, then f x will be also subset of f y y, because this is same, I am taking intersection and with a set where this is basically subset of this. So, then this must be f x should be subset of f y. So, then what I have effectively shown that this function which is corresponding to sat e g phi is a monotone function, and since monotone function I have already proved that it should have fixed point. So, I will basically if I calculate my e g phi with this, I will reach to a fixed point. It means all the states where this should hold, I am effectively correctly identify them. Okay. So, that is the overall idea, and similar way you can actually prove AF phi and EX phi. I am not going this detailed proof here, but I hope the correctness concept is clear for model checking algorithm of CTL. Okay. With this I conclude today's class. Thank you.